Hello. So thank you all for coming. So I'm present in the room and online. We are really happy today to have Gustau CAMPS-VALLS, who is here. So Gustau is a full professor of electrical engineering at Universitat de Valencia. He's the group leader of his team, distinguished lecturer and IEEE fellow, and he's also an ELIS fellow and program coordinator. He's also leading and still leading really large research projects, ERC projects. And today he's going to talk to us about AI and Earth system. So thank you very much, Gustavo, for coming. I will let you do your talk.
Thank you very much, Rani, for the nice introduction. Yeah, today it's really a great pleasure to be here. And actually, I had to tell, of course, an anecdote. This is my first talk, I would say, in 2 years or so in person. So I do not really cannot remember very well how to perform in public. I almost forget about it. Well, anyway, today I'm going to talk about recent advances that we have been doing in the lab and also elsewhere in AI for modeling and understanding. I will emphasize through the talk this word understanding rather than predicting or fitting. In particularly, the focus on in our lab and also in other labs is on the Earth system science. So I will touch upon different topics. Mainly, you have it in the slide, in the introduction slide, the physics of machine learning, interpretability, and causality. How we are doing these things in the Earth system science. But of course, you can figure it out that these methods that I'm going to present will be useful also for other domain sciences. Okay, so let's see if this works. Okay, bonjour. This is my first icebreaker slide. And a bit of promotion of the city and the group. This is Valencia, the region, and I'm flying back and forth from Valencia to Paris every now and then. So we'll have time for chatting in person around the city here. The group is the image and signal processing group. We are roughly 40 people and growing. We are always hiring smart people. So feel free to come and visit and chat. And what I'm going to present in this lecture, it is the result of many years of collaboration with many different people, with many different labs, and also with the support of many different companies and organizations. So of course, I have to acknowledge all of them. The outline of the presentation, I try to split this presentation in 3 parts. The first one is a more introductory part on how things are done typically when you want to apply machine learning for the earth sciences. I will give you a bunch of examples, and then I will try to put to put forward the main problems that we are already seeing in the mere and ad hoc application of machine learning for the earth sciences. Namely, are the methods that we are applying or the models that we are developing consistent with the laws of physics? And then for the third part, I will ask further, are they explainable? Are they interpretable, robust, or they are just like black boxes that fit very well? And then of course, we are actually looking for the main holy grail of learning or understanding systems, which is causality. And I will tell you some examples about how things are done. Okay, let's go for the simpler, more introductory part, the machine learning for the earth sciences and how things are done. Well, this is our little lovely object that we are interested about. This is the earth. It looks very innocent, very, very simple, but it is not that innocent. It's very complicated. It is a highly connected, complex network system with tons of processes going on at different temporal and spatial scales. And we want to not only model the system, but also understand it and to find projections about the state of the system in the future, right? And for that, we use a lot of physics, but also now very recently in the last decade or so, the impact of AI has been tremendous in this scientific domain. So here you have some instantations in a very nice video of different variables that we are interested in monitoring on our system. for example, methane, evaporation, carbon dioxide, etc. We call this data cubes. Okay, so you have a cube that has spatial but also temporal coordinates, and this is a constant influx of data, massive data. This is just an example of a particular spatial and temporal resolution, but you may imagine that you can go from meters to kilometers, depending on the sensor and the acquisition system. And this is how this system is actually helping us to monitor, for example, vegetation. In this case, you can see how the gross primary productivity is evolving in this region of Africa. So you can actually capture how vegetation is doing and the health status and vital signs of the earth are performing. Of course, the variables are interrelated. So it is not just one unique variable, but it is a multivariate problem, multidimensional, and spatial temporally correlated at different relationships and at different scales. Okay, so this is the main goal. So how to extract information out of these large data. And we do many things. For example, we use these data cubes in order to predict the crop yield from space. So you can actually measure and estimate what will be the harvest of a particular season and a particular crop of interest. But you can also be interested in monitoring our coastline and the ocean, for example, by retrieving parameters of interest like chlorophyll content, or maybe water quality indicators or things like that. Of course, a lot of people is working, and we are also doing so, monitoring the atmosphere, for example, or the air quality indicator. Here, for example, you see a European map of the retrieval of NO2, this dioxide nitrogen, nitrogen dioxide in a tropospheric column integrated. And you can see that, well, for example, Paris is not the best place to live in Europe. So this will be important to not only, it has a lot of implications on the, quality of life and also the health issues and how to monitor how the population is doing. And there are many different trace gases that can be monitored, and many different algorithms have been applied for not only modeling but also predicting and forecasting this quantities, right? But we are not only interested in estimating, but also in detecting what is anomalous, what is strange, right? We are living in an era where this system is largely evolving, and there are tons of different extreme events. And this is one particular extreme event. This is an example. In the year 2010, you can see for the months that the algorithm is trying to detect what is anomalous. I mean, what is the temperature anomaly with respect to previous years, and it has detected a particularly interesting blob here around the region in Russia that it can detect in time and delineate very well in space. So you can basically retrieve some spatial temporal anomaly descriptors, let's say, and this corresponded to the 2010 Russian heat wave. This was a massive heat wave that caused a lot of losses in terms of crops and but also casualties. And this way we can not only delineate and detect, but with machine learning we can anticipate this. But for that we need a lot of data, a lot of computers, and a lot of efficient models for doing so. Right? Okay, and in this context, we are well aware that machine learning is playing a big role these days. But the main modes of machine learning is always the same, right? Give the power to the data, and with enough data on large computers, you will be able to solve any problem at hand, right? I'm gonna summarize, like, in very 3 simple slides, what are the architectures, or what are the methods that have been used in machine learning for year sciences. I noticed before that we are dealing with spatial temporal data structures, right? So typically people started applying convolutional neural networks, but then they realized that the process is also evolving time. So
this is a standard architecture that people is using, which is the combination of a convolutional neural network and an LSTM layer, in order to, to combine both modalities of the data. No? And this has been used for detection, but also for prediction of biophysical parameters. But you can go also probabilistic. And in this arena where you have tons and tons of data to predict on, but you don't have too many data to learn from, so your databases for training are typically very small because they come from terrestrial campaigns, so you don't have a lot of time and effort and resources to sample properly. In these situations, Gaussian processes and probabilistic learning has been playing a fundamental role. And now Gaussian processes can scale very well, let's say to 100,000 points or something like that. And in this case, for example, we were able to deploy a GP for cloud detection that we designed this Gaussian process to be efficient, but also to incorporate the spatial and temporal structures in the kernel function. But as I told you, it is important to account for the space and time relationship. And this is commonplace in many areas, not only in neurosciences. You may think on climate informatics and neuroscience, in signal processing, in natural language processing, of course. So, of course, these combinations of CNNs plus LSTMs, they can work very well. But now there are novel methods and approaches that promise like great advantages. Note, for example, that we here in this field, we have like a mismatch between the resolution that you're able to acquire, let's say, with a satellite sensor, but then you don't have for every pixel, let's say, a particular estimate, a particular parameter. You have maybe just one measurement for the whole area, for the whole parcel or region. It is the case, for example, of crop yield estimation, right? So you have a production number per parcel or per area. So how to work with distribution data, how to work with distribution to label, not just label to label, right? Not just feature vector to label. So this is the case of distribution regression methodologies, and they have been using quite a lot in the recent years. And also, of course, deep learning in all its variety and deep Gaussian processes as well, because it is very important. I would like to highlight and to emphasize this, that in this area we are very, very interested, not only in the point-wise estimate, but also in the confidence of the prediction. It is even more important for us. Okay, so apparently we are all done with machine learning for the sciences. Everything, proceeding correctly because we can predict, we can classify, we can detect, everything is solved, right? So yeah, but it is not actually the case. If you look at the literature, not only the 99% of the papers that they just focus on improving the accuracy by 1% or 2% or something like that. If you look at the Nature and Science covers, it looks like AI not only is excelling in many different fields, but also it's actually promising to transform the scientific discovery and endeavor as a whole. So with data and models, in principle, you should be able to do everything, right? So this is the big promise. But yeah, it is also the same thing in your sciences. We have data, we have models, we have computers. In this paper, in this Nature paper, and in this book, we are actually approaching the problem from a different perspective. You can tell the title. You can tell it from the title: deep learning and process understanding. So what we are promoting here is the interaction between these two, in principle, irreconcilable fields, right? On the one side of the pendulum, you have deep learning that only focuses on data, and data is enough, and that's the whole ground, and everything is solved with data because you expect the data will act as an efficient regularizer. And on the other hand, you have on the other side of the pendulum, you have physics that rely on laws that are invariant. So it looks like they are kind of irreconcilable, right? But in this particular perspective paper, what we were actually interested in is in trying to merge these two fields in order to make not only models more efficient and consistent, but also to learn something about the system itself. Okay, so this apparently, I mean, the deep learning era has come and works perfectly fine as well in earth sciences, but only when some things happen. When you have a strong spatial and temporal correlations, that happens. When you have big data, when you have cheap computing and fast and scalable machine learning models, and it is typically argued that machine learning for earth sciences or machine learning in general is working because in reality you don't need any extra knowledge, or you are only interested in high accuracy. You are not particularly interested in learning anything. So side note, why do we call it learning, right? So you should be understanding something. No? And then, since understanding is the system is irrelevant and you only are concerned about accuracy, well, of course you're done. But if you are doing more, you should be quite concerned at this point. And these are like the deep learning or the machine learning challenges that I foresee in the future, and actually they're already happening. The first one, and it is quite annoying when you speak to physicists, is that models, machine learning models or deep learning models, do not respect necessarily the laws of physics, like the conservation of mass or energy. And this is quite annoying. And actually, nobody will buy a deep learning model that does not conserve this fundamental constraint, right? Then the other question that I would like to read in this talk is that these models, apparently they work fine, they predict well, but how do we know what these models actually learn, right? So are they interpretable? They can be explained somehow. And the third one is that by training a particular model, you are assuming that X is always causing Y, but there are other interactions and there are other cause and effect relationships even within the same X's and Y, right? So these three topics are the topics that I'm going to talk about in this presentation. Of course, not everything's dark and obscure and problematic. There is some light at the end of the tunnel, and we will try to see what is being doing in the machine learning, for example, for incorporating physics, interpreting the models, and jumping from the pure mere fitting paradigm to the understanding and causality. Okay, so let's move on now to the part 2, which is the machine learning should respect physics. And the idea is here. The idea is very simple. So most of the times you want to learn F that takes X's and then tries to detect Y's, and then in this new field of physics-aware machine learning, you try to incorporate some laws that should predict, that should be respected somehow, right? You will find the term physics-aware machine learning in different similar concepts, like in physics-guided, physics-informed, or physics-constrained, or even science-guided, right? That will depend on the author and the community, and it is just like a very subtle distinction, and of course, promoted by your own interest. Are you believing that the machine learning is the model, and then you incorporate the physics, or the other way around? It is physics that should be fixed, and then you can enrich the physics or learn new physics from data with machine learning, right? So this I wanted to make this clear distinction. I will be referring to physics-aware machine learning because my main predictive model will be a machine learning model, and then I will try to constrain the space of solutions with physics. Okay, the truth is that the community is turning to this physics-aware machine learning quite vastly. Everything started, let's say, with this nice presentation I attended some years ago in ATU. So you can read models with a data are fantasy, data without models are chaos, or kind of, right? I mean, it's very provocative statement, but anyway, this is the motivation for what we are actually doing in physics-aware machine learning. And here we propose like a very simple taxonomy in the ways that machine learning and physics can interact. For example, in the box A, you have data and model interactions or blending. So you want to combine in a single model both observational data and simulations coming from models, right? From physical models. There are many ways of doing this. So in the box B, maybe you're interested in another type of communication between machine learning and physics. You want to replace the physical model with some surrogate model coming from machine learning that it is more efficient, faster, right? And then we can inherit some properties of the machine learning model. In box C, maybe you're interested in learning some obscure heuristic parameters of physical models, because do not forget, physical models are like machine learning models, are just models, right? So just an approximation of reality. And then maybe in some cases, you are interested in estimating those parameters more efficiently, or let's say more objectively. And the fourth thing I would say is that of learning physics from data. I will show you some examples of methods that are. There's someone asking something, or so yeah. So let's move on. I will just try to summarize some examples of every methodology here. And I will start from the simplest case, right? The simplest case is to reformulate your loss into a physical law. How do we do this when you want to incorporate a particular prior in your algorithm, a particular inductive bias, if you want? Well, just plug in a new regularizer, and people who have been doing so in this context of constraint optimization with physics-based regularizer. Okay, like in this case, for example, the authors were interested in predicting the temperature at different layers in lakes, and they noticed that they could do it very well, but there were some erratic behavior and some erratic predictions as you go through the layers in the lake, right? So they observed this and said, okay, we know that the depth and the density temperature are related, and as you go through the layers in the lake, the density should increase. So, and this is related to temperature. So they designed a regularizer that imposed as a third term in this physical laws that eventually was just penalizing all the discrepancies or violations of this simple physical rule, physical law. Okay? So that was simple and it worked very well. And what the authors also observed is that the model could extrapolate to unseen lakes, because this is a fundamental law that it has to be fulfilled in all the lakes that we can. Okay? Well, we came up with a new approach because in the previous approach, the authors basically proposed L2 norm, mean square error, for measuring these discrepancies with the physical law, and they could only use like one law at a time. In this particular case, what we reformulated this was in terms of kernel methods, and instead of talking about MSE or correlation, we used an independence criterion called ASIC, the Hilbert-Schmidt independence criterion, that it is zero if and only if the two variables, the prediction and the physical law, are fully independent. Okay? So what it is nice is that instead of a neural network, you use kernel methods, kernel regression, everything comes in closed form solution, which is only have to resort to this particular inverse that you see in the slide. And what it is also interesting is that it is very, very clear that physics here, motivated from the field of algorithmic fairness, by the way, it is acting as a very explicit regularized field, right? A sum over the kernel function or the kernel method. And of course, we came up with a probabilistic version interpreted from a Gaussian process, so we can derive the Gaussian process.
If I interrupt, can you explication of this independence between just the states that we want here? So the constraint optimization comes very clear.
Yeah.
And here, what are you doing?
Yeah, it's exactly the same thing. Here you see that it's omega. Yeah, but it's not. Okay. So you have this omega, right? That it is basically an NSE, what the authors propose here. What we are replacing this is with well, there have been some other authors that propose mutual information, but again, it is costly. Yeah, you know, you have to do some parameters, and it is univariate, right? And in ASIC, we are doing exactly the same thing, replacing this omega with independent criterion. So instead of measuring, let's say, error, we're measuring independence. Of course, you turn this plus into a minus and promote dependence. Okay? I will show you an example. In this case, for example, we are interested in predicting temperature anomalies in years, right? And you are ingesting different variables, like from anthropogenic factors to natural factors. And then you want to check what is the important thing here, no? What is driving this temperature anomaly increase, no? That we have been observing in the last decade, no? So basically, you develop different models for predicting temperature anomalies. Well, and at the same time, they should be independent of the natural factors, or you develop another one that should be independent of anthropogenic factors. Okay, and then you can see that you cannot actually predict well while being consistent with the hypothesis that the humans do not have anything to do with this, right? And then you can plot this, let's say, Pareto fronts of accuracy of the model with consistency, with physical consistency. And you can summarize these curves into basically just like some area under these curves. You can summarize this as a kind of accuracy consistent score, let's say, no? And what we basically retrieve is that the most important variables in order to explain this increase in temperature were the aerosols and the greenhouse gas emission, which was suspected. And this is a very simple example, okay? Okay, let's jump to the second approach, where we typically have data, observational data, but we also have some models, let's say, either climate models or radiation transfer models when you're working with remote sensing. No? In this case, we wanted to incorporate those, to design a machine learning model that could actually blend these two sources of information. We derive a particular Gaussian process called the joint GB, the joint Gaussian process, that it is able to ingest and to weight or downweight each piece of information and learn the hyperparameter that considers this or that more important in the for prediction. And what it is nice is that you can work with different domains, with different ranges of domains. For example, in the figure on the left, you can see that the dashed line, this is standard GP, it is performing very well because it passes through the training set, which are basically the dots in blue. It does very well, but then what happens when you are trying to predict outside the in-sample domain? Well, what happens is that predictions are tending to the prior, so zero mean prior, and then the confidence intervals they increase a lot because you have not seen any data in those regions, so you are completely uncertain, right? Then, on the contrary, when you embed new data coming from simulations, and simulations are nice because they can encompass all the range, right? Then the algorithm in solid red line here, it performs very well there because it is actually given like a lot of credit to the observational data. And then outside the region, it says, okay, I don't have real data, real observational data. So what do I have? I have simulations. So then I will try to follow the simulations, right? So it is actually compensating these two sources of information. And then what it is also nice is that the confidence intervals diminish. So we use this simple GP into a particular problem in remote sensing, which is the prediction of leaf area index. So how many leaves do you have in a square meter, right? Roughly speaking. So we use satellite data coming from Landsat 8, and then we use simulations from a particular radiation model called to say. So in the end, at the end of the day, you have both X and Y coming from observations, but also coming from simulations. And then we have, interestingly, 3 campaigns in Spain, Greece, and Italy. And then you can see here, like in this type of plot, that the blue dots are coming from simulations, and the red dots and the green dots are coming from observational measurement, from in situ measurement. And well, in some cases, you have your domain completely filled up, and well, methods are performing, GPs or joint GPs are performing pretty equally. But what happens when you have these cases, like in Greece, where there is like a big mismatch and not all the expected distribution, theoretical distribution in blue is completely for that. So what happens in those cases is that the confidence intervals are they increased quite a lot. And then also you can take that as a kind of like extrapolation indicator. And it is also nice because you also learn from the GP a parameter that tells you, hey, in this case, you should not trust your institution, right? And this was actually after a lot of discussions with the Greek case, we were able to certify that there were like some mismatch on different, protocols that they were not fulfilled in this measurement campaign. So it could learn something, right? Okay, there is another way to incorporate physics in machine learning. And in this case, again, with Gaussian processes, we try to incorporate ODEs, ordinary differential equations. Most of the times in physics, we are working with differential equations, either ordinary or partial. But this is a very nice Gaussian process that essentially looks and resembles sort of a neural network. You can see in the cartoon on the left. But essentially here, the input nodes, they are not actually observed. They are modeled as Gaussian process trials, and then you have a number of latent forces, let's call them. These are latent forces. This is a parameter to tune. And then what you assume is that the combination of these latent forces, the linear combination, are passed through a linear filter, this H filters, plus some additive Y-back Gaussian noise will give rise to your observational data. Okay? And then what you learn is many things. I mean, you learn the latent forces, you learn the parameters, you learn the upper parameters for the noise, you learn many different things. Why is this useful? Well, this is useful, for example, in this case. In this case, we were interested in predicting moisture, soil moisture. Okay, coming from different sensors, from different satellite sensors. And every sensor is measuring differently, right? You have also different temporal scales, different revisiting times. So you have like a very big problem of uneven sampling. And then what happens here is that these are the in situ measurements in that particular station. You have here predictions and also the small data. This is a one satellite sensor, ASCAT sensor, and the answer 2 that you can actually see that in the early 2 years, you didn't have that sensor. It was not existing, it was not flying. But the model is able to extrapolate and to transport information from these sensors to this other and give you, of course, all the advantages of GPs. Not only the good predictions in this case, but also the confidence interval, right? But moreover, I mean, when you look and zoom in some particular pieces of this actually, this latent force model is actually performing quite well. But what about the latent forces that this model has learned? Well, remember that this latent force model GP is only using time as input. Okay, nothing like that. Other than that. So when you look at this, when you look at this latent force that has been learned, you immediately recognize that it has learned something related to precipitation, which is quite intriguing because the model never saw precipitation as input, no? But it is learning that precipitation is actually a driving force of soil moisture. Of course, if it rains, the soil is wet, right? And this was the basic relation that we were encoding in this filter that I told you about, these H filters. These H filters are basically derived from the first order ODE we calculating the decay in slow motion as taking a precipitation, let's say, or a spike as an input response of the precipitation. Okay, so that was nice because you could learn some kind of driving factors. I mean, you could, for example, learn precipitation pattern just by looking how wet the soil is. Right? Kind of not strictly, but really close to causality. Right? Then the fourth paradigm, I would say, is hybrid modeling, we call it. And in hybrid modeling, this is a new term, but it is actually very old stuff. You can see this paper in 2004, where the authors in this journal of computer science and chemical engineering, they were interested in monitoring some particular parameters of a chemical process. I'm not really an expert on those things, but it was really, striking to see that figure in the paper that this is what we are actually interested in now these days. Oh, it makes it look like hybrid model, right? Because you have a network and then you have some other ancillary variables that are coming from a physical process and they combine everything. No? And then I was really, really curious about what happened with this sort of literature. They were all two papers. And then I discovered that this disappeared. I mean, this vanished in the big literature body of literature, mainly because at that time you don't have automatic differentiation. So you could not learn these two models at the same time, end to end. So you have to fit one, then fit it to the other one, and then alternate between them. And that, of course, it is not practical. Right? And then this brings us to propose like a big family of methodologies for hybridizing, if you want, to the definition. And this is the idea. The idea is very simple, is to design layers in neural networks that incorporate some constraints that should be reasonable and should be certifiable in physics, right? For example, you have this very nice example on the right. In here, the author used an encoder-decoder architecture in order to predict motion fields. And then, thanks to the use of a physical model, they could actually work these motion field predictions in such a way that they should be physically consistent. And then you can learn end-to-end everything. Right? That was a very, very nice exercise, a very nice example of this hybrid modeling paradigm. Yeah, more, and you can tell from the literature that in physics we are always working with differential equations, and this is another standard approach in hybrid modeling, which is called physics-informed neural networks. Essentially, here instead of just developing a neural network, what we do in SIR, what you know is that there are some intrinsic relationships between SIR, basically driven by some differential equations that you know, or even some conservation laws like this E4, right? In E4, they're basically trying to balance some to keep under control an energy balance, right, or a mass balance, for example. And then what is nice is that you can design this architecture and the relationship between the differential equations and the intermediate operators. They can be cast as a neural network as well, a coupled neural network, right? So what happens with this neural network in here? So, well, you get your SIR predictions as well, but you can also learn hyperparameters of the different networks, which are really cool because you could say something about the alphas and the betas. So you could be more, let's say, consistent and objective by learning those hyperparameters, the parameters of the ODEs through this. Okay? So that's a very, very nice example in the years. Of course, I told you, okay, yeah, we have this problem that models are complicated, they are costly most of the times. So there is this field of emulation or surrogate modeling that tries to replace a physical model with machine learning. This is a simple, nice, and neat regression exercise. So you generate data from your model, and then you have X and Y, and then replace this mapping with a machine learning. What do you mean by that? Of course, speed, because then once the neural network or the GPU is trained, then you can start predicting like crazy and getting like a lot of simulations, almost like for free and very very cheap. But then you also inherit some properties, let's say, of the machine learning model that you are being used. For example, if you're using a Gaussian process, you could derive confidence interval for the simulation, something that you could not do with your in principle with your physical model, unless, of course, you do some permutation analysis or and then at the same time, you can learn something about what are the important parameters in the physical process, no? Because you can run this sensitive analysis and you begin to compensate. Okay, and then the last example, just before the coffee break, is about discovering equations from data, and this is a very simple, very neat example of how you can do this under certain circumstances. So authors here put it the problem as a regression problem, as a sparse regression problem. So imagine that you have this very nice and simple, let's say, Lorentz tractor, X, Y, Z, and then you can basically, interpret or discretize the derivatives. So you have the derivatives of X, of Y, and Z, and then you construct your basis, let's say, with your design matrix, if you want, your phi of X, has all the possible or plausible combinations of X, Y, Z. So you can compute that, right? You can do 1, bias, the X, the Y, the Z, the X squared, the Y squared, X times Y, X times Z, whatever, right? So you build this phi, and then you learn these sparse ways with, for example, lasso. Okay? So that's what they proposed, and it actually can recover the attractor very well. And this works decently well, very, very well in low noise regimes. But at the moment that you incorporate some stochasticity, then the model is actually failing and is very sensitive to this. We were super interested in applying this in our sciences because some processes are known and you want to know. You want to know not only these coefficients of governing the dynamics of particular ecosystems in this case, but also remember, as soon as you have a differential equation, you can start asking questions, right? You can start doing perturbation analysis, and you can say things about stability or chaoticity or projections, etc. Right? So in this case, we collected a good bunch of data, temperature, GDP, moisture, many different variables, right? Many different variables, and then we were able to compress them in 2 main axes, just for calculating the system. And it was very nice because with just 3 components, you could summarize the status of these ecosystems at 90-something% of variables. In this case, just for simplicity, we plot only the first 2 axes and for different ecosystems. You can see here, maritime, continental ecosystems, etc. And these are basically the trajectories, and these are the equations that you are able to learn, and then you can start analyzing the way. Of course, this is super preliminary results, and we have to scrutinize more the Brown estimation. Okay, so I hope there are questions because I told you a good bunch of stories. So we have like some more 10 minutes or something to discuss, or we have to take a couple.
Okay. So I have a question precisely about the last slides you were showing. So maybe it's just on point. But so first, what's the difference between this discover or the EPDs that you're presenting as a 6-point and the one that I think you were presenting earlier in terms of hybrid modeling that was using the physics-informed neural networks, in which you can also learn the parameters of the PD. So this, and also I think one of the points of that was sold. I mean, I never used those models, so maybe there's something I don't know. But one of the points that was solved on those physics-informed neural network used to discover the PDEs is that thanks to automatic differentiation, they didn't need to compute the derivatives by finite differences, and so they were much more robust to noise. So I was wondering if this is something you had explored also in this context.
Well, the two questions, right? The difference is very subtle. Here, you're assuming a deep design matrix with all the possible relationships, because you are uncertain about what are the intrinsic relationships. It is very subtle because on the other case, in hints, you're assuming the right equations that you want to learn, right? And you're more interested in the parameter information. But it is very, very, very subtle. It's very, very subtle. Then the second question was the noise, right?
Yeah. So I think there is a connection, but I was actually cited in the PhD theory of somebody who has done his PhD thesis on this. This is my only knowledge on this. But they were precisely combining the two, the sparse regression with the pins approach. So they were both discovering which of the terms they should keep in the PDE and the value of the coefficients. So maybe I'm not sure it scales. I'm not sure it's, but it feels like it's a connection between the two.
Yeah. Probably there's a connection. I mean, I think that the connection is can be traced because essentially here, I mean, in the end here you're using a lasso, you're using a linear regression, but the basis is nonlinear. In the other case, you have the differential equations that they are explicitly put as basis, right? Because in the end, let me see. Here, here, these would be the alphas and the betas corresponding to the ways that you're learning with Basel, let's say, with the CB approach, the second approach. Well, here you're already computing finite differences, in order to feed the team. So the connections is, I think, it's because of these two issues. No? The only thing is that here you are, in my opinion, you are completely certain that these are the equations to learn. And while in the other case, well, of course, you can do like basic problem or whatever, or maybe consider only some of them. But the solution is more ample. Simpler in the case, in a way, because that's a lasso regression. But sincerely, I don't have experience in this thing. What I can tell you from the noise is that, at least for this case, it is very, very, very sensitive. And the selection of the basis. Wow. In real cases, I mean. Yes. We have been playing around with different Gaussian processes for coupling and for tackling the nonlinearity issue, and also because in Gaussian processes the derivatives can be expressed as algebra as well. And then it is more amenable to do the thing. But still, very sensitive.
In that case, based on the SAR of the data
It could be. Yeah. The only thing is that you're in the previous, I mean, in the constraint optimization approach, you would be learning a standard network, and you would be learning parameters in the connecting layer, right? Here, everything's coupled, and you learn this coupled.
Just quickly repeat the question.
Okay.
No problem. So I had a question about the real life model with the age and everything. You know, as a signal processing guy, I love it. And so basically, you learn
you do source separation, but you simultaneously learn the source. So the one here, but you simultaneously learn the source that are the F.
Yes.
And also the physical convolution.
Yes.
Non-stationary convolution with the H. That's what I thought.
Yes, yes, because I mean this is just a cartoon, this is just a design, but what happens is that note that if you model the latent forces of GPs and all the operations are linear operations and linear filters, in the end is a GP. So it has an associated kernel. So you can, I mean, after very nice sunny afternoon with a glass of wine and integrate them twice, slowly, by parts and all that stuff, you can come up with equations that you have to, I mean, with the kernel that you have to optimize.
Okay.
Yeah, it's very beautiful method. I think proposed by Mauricio Alvarez and Levi and Roman. Okay. We have been exploiting this.
What's the first step? What's possible to do? That's explainable. What can you give us? What are the limits? As system is a complex system with a lot of interactions. So, how much data do you need? How much do you make the prediction? What's the prediction power that we manage to achieve nowadays, especially what are the scales of the scales?
Wow, that's a very challenging question. I mean, the question was about what is this techniques now on the machine learning real applications? What can we predict and what can we not predict? And it is a very, very, very multivariate question because it depends on the application itself. I mean, and the sensors that you want. There's people working with optical only, and then you have the problems of clouds, because then you have to observation, and then you have the problems of feeling is, and then in this arena, for example, GANs and normalizing both have been used in recent years, improving quite a lot these gap filling approaches. Also, callers and autocallers have been used in order to be able to improve as well. Also for detecting anomalies. It is complicated to say, okay, we are fine, or yeah, there are lots of challenges because the field is evolving so fast, and it is also depending a lot of the application and the spatial and the temporal resolution that you have that plays a role. There's also some a lot of applications of machine learning and institute data only, right? And learning about those. People working on a global scale, so that you have to go to force a spatial resolution. But then you encounter the problem of sampling because you only have measuring stations in the reach north, let's say, right? And then what happens when you try to calculate to the south, right? Or to the tropics where so there are like many problems of sampling, problems and many challenges of extrapolation, because you don't actually know when and where are you extrapolating when you derive these beautiful global maps from data. So that's why still I see a lot of, let's say, reluctancy or skepticism from the physics people machine learning, because I mean data, even if you have access to millions and millions of data points, is not enough. It's not enough. The validation strategies of parameter tuning improves information. There has been some recent methods from some advantage, and not to speak about climate. That's another story, because as I told you, the system is evolving and it's ever changing. So, and this is the big failure of machine learning, right? We are not really prepared to work with petabytes of data in a constantly evolving system in space and time, right? So full of anomalies.
Hybrid model, but then we have a hybrid solver, like many element method.
I think, well, yeah, if I understood correctly, you have a hybrid model, but you don't have a hybrid solver. Well, most of the people, when they approach this hybrid modeling approaches, they use automatic function. A lot of people have been moving from Python to Julia to space, and they have found like nice solvers in that arena. I don't know, but most of the times it's find the structure, the architecture of your model, and then apply it. Yeah, unless you go in always at the end it is linear algebra, right? With that comparison methods or finding the or and apparently everything's solved now, right? So we have models that can work, that can scale, and now we have this playing field of incorporated physics. That's good. That's good. But what happens inside the model? I mean, explain what they're actually doing, or they're just speaking. That's it. And maybe we're looking like 2 decades or 3 decades of our life. And the same way that we lost almost a century thinking about correlation. Okay? I will speak a bit about causation. Okay, so let's go for this part 3, the last one, which is try to develop models that are transparent as possible, are interpretable into one, explainable, and causal. Particularly interested in those. Let's see what happens here. So let's jump first for the explainable AI field. Probably we have already heard about this field in machine learning and deep learning in particular, because you can really see that the main developments are that there's a lot of developments in deep learning, and most of them they end up with a big monster over parameterized with millions and millions of weights there. That fits very well, and that is amazingly well, right? So you would say, okay, and what are these weights for, right? I mean, it is like, so what the hell are you doing with those? No? So this is mainly the field of interpreting what the model is actually learn, right? The interpretability is an issue. And we want to discover what are the intrinsic rules or the tricks and hacks, the tools that the machine learning is actually taking. No? So there are many different approaches to this problem, but in the end, the main objective is to try to either explain what's happening between the input and the output, or opening the box and looking inside. Right? You have this sort of opportunity here. I named this as deconstruction. So you want to, make pieces out of the big piece, no? And it is not, I mean, it is a big field, actually. It is not just that we are starting with that. There are like probably 10 to 20 pages of 20 or 100 pages each with 500 references each. And by the way, I didn't check that today. Probably there's another one. So it's quite, challenging, right, to keep up with the field. But I would say that there are basically, in a very simplistic way of approaching the field, you have like 2-3 different forms. You can either construct a self-explanatory model, or you can try to open the box and try to see what are the filters doing, or you can replace this very complicated model with something simpler that it is more amenable, right? There are many, this is something. Or you can just resort to standard ways instead of using inference as always, and derive sensitivity maps of the input-output map, right? So these are basically the main strategies in the field, but there are many others. So let's start with simple examples in the Earth system side, right? So the first approach was the sensitivity analysis that happened like 2 decades ago, or even 3 decades ago, different flavors. But essentially here, the objective is to derive a ranking, right? A relative relevance feature ranking. And this is the standard approach. You don't care too much about what's happening inside the model, but you just want to summarize what happens when I perturbate one input and see what happens with the output. If I perturbate it and the output changes, is that because this input is actually important, right? Or if I annihilate it, no? Or if I just put everything to zero. I mean, you start disturbing the inputs and see what happens with it, right? This is the standard approach. And that was very nice, and it is still very useful because it works for whatever machine learning model. So it is not model specific. You can apply it to a network, to a forest, or whatever. No? In recent years, we came up with this analysis in this +1 paper focused on kernel methods, because we noticed that most of the times you only want to resort to derivatives from each problem or negation to explain what's happening in a model, right? And what is nice of kernel methods is that you can actually derive those in explicit form. And they only depend on the kernel functions, because the weights of the particular function, they are fixed already because they are learned. And we apply it not only to regression processes, but also SVMs. They play a role and they can be related to the margin. Then you can also apply it to density estimation with kernel entropy component analysis. So there's also a connection between the derivative and the reach with the information content of the distribution and density estimation. And then we also jump into applying these techniques to explain dependency. And we apply it to this kernel method for dependence measures that I told you before, right? So you can actually derive maps of sensitivity of a dependence measure. And you could use that, for example, for maximizing dependency or minimizing dependence. And we apply it to, for example, for detecting anomalies in temperature. So when the derivative is changing a lot in space of time, is because something anomalous is changing. It is happening. Okay? So you can summarize these dependency measures in time and identify what is actually changing. In a very similar fashion to the video that I showed you at the very beginning. Okay, but what happens when you have like unsupervised models? For example, you have a density estimator, and how do you analyze those? Because you don't actually have like specific mapping X to Y, right? So this is the case of this encoder-decoder model that we developed for detecting anomalies. In particular, we focus on the rational feedback that I showed you. So the algorithm is basically deriving like a latent representation with an encoder-decoder strategy. The encoder is a particular instantiation of fast and slow neural networks, because you have different samplings in the different variables that you're ingesting. Remember, we are ingesting cubes of moisture, GPT, transpiration, etc. And there are gaps as well. So you want to incorporate all this spatial temporal information. So it is basically paying attention to the different aspects of these cubes in space by attention mechanisms and appearance feature structures and emotion, because you are dealing with different kinds of processes happening at different times. And then what happens? You learn how to reconstruct these cubes well with this specific encoder. Then you learn a latent representation. And then what? Well, we want to derive an anomaly score out of this latent representation. So what we did is computing an anomaly score after Gaussianizing with a Gaussianization flow. So you can multivariate Gaussianize this distribution, and then it is very simple to derive the score from the probability that you are able to make. The point is that this method works very well. You can see here in the curve that the Russian feed rate, at least the onset, is actually very well captured. There are, of course, some false alarms here and there, but we were not only interested in detecting this drop that we can reasonably detect it. It is a very massive and quite evident heat wave impacting the area, but we wanted to understand what the model has learned, what are the features and the control scales that are important for the predictive or anticipated trial. You know? And this is what happened, right? So we could derive sensitivity analysis out of the encoder by just applying integrated gradients. This is a technique typically used in explainable AI. So accounts for the derivatives of the function, and then what you can do is to derive this sort of maps that tell you which are the variables that are more active, are more important to time. Okay? And then of course you can transpose this in. So what is nice is that, for example, here around the time of the event, essentially liver index were suffering right after the event. Then air temperature was popping up, of course, and then lower decreasing evaporation GDP, and then what was also impressive is what happened before, just in case that we can anticipate it, and what happens after, what are the impacts, what are the climate impacts of this crop. And then you can monitor this according to what the model has learned. This is an important advantage of trying to explain what the model has learned. To learn from the past and then to predict from the future. Well, the second approach is very simple. It is just to decompose your model. Well, if you cannot, if you're, of course, you can work with Gaussian processes, it is very easy because you know that in Gaussian processes, as in any methods, everything boils down to the design of our thermal function. And in this case, we were very interested in predicting crop yields in the Corn Belt in the US. Here, where it's a very massive region where you have corn, of course, and wheat and soybean, and you want to estimate the production year-wise for every county. Okay? So we were ingesting all kinds of variables, like vegetation indices, time series, vegetation optical depth, soil moisture, all kinds of meteorological variables, etc. And then we wanted to estimate this crop, right? But there are like non-stationarities and non-linearities and different non-sources in this process. Every county is measuring in different ways. There are some missing gaps here and there. There are some trends because of the because of irrigation strategies or different agricultural practices. So we wanted to design a very simple and neat curve function like this one. So we basically used a combination of three curve functions: a linear one, an RDF one, and a noise term. So you can learn what is the relative relevance of the linearity, let's say, to account for non-stationarities and the nonlinear with a mu. Then you can learn a sigma parameter for the scales. And then you can learn the sigma n for the noise, how much noise do you have per county. Okay? And then what is nice is that, okay, you can do a good job. You can predict quite well these crops. But then you can also explain, right? Because when you predict and you can visualize which are the differences between the predictions and your observational data, you can tell, for example, that there are like big differences between the maximum and the typical ingredients, also some deviations or some shifts in the vegetation optical depth. This variable is accounting for, let's say, roughly speaking, how much water the plants are accumulating, okay, for growth. So you can tell some differences and when actually happen, right? So you can anticipate some problems in the growing status of the vegetation. So moisture, and then what is also nice is that just by looking at the model weights, the parameters of the model, that gives you kind of an idea of what are the most anomalous or most erroneous predictions. Right? And this actually happened over here, and this corresponds to a particular country that was very, very affected. At least the harvest was very affected by the severe drought in that year. So this is simple model, but by construction we can actually explain what's going on. Okay, there is this third family called model distillation. I'm sorry, but I don't have any example in this. probably there's some, but I didn't find it. And I think that this is a very promising direction, by the way. Essentially, the idea is, okay, I have this big monster, this big fat neural network that I don't want, but I have to, right? And then I want to replace it with something simpler and more explainable. So people have been ideas how to, sparsify these models, simplify them, approximating with random forest or decision tree, something simple. Then, okay, give us some accuracy, but at least they can get what's right. So essentially, it works in a very similar fashion to start a technology or emulate, right? But instead of simulating a physical model, we emulate okay, and the fourth approach is opening the box and looking inside, So yeah, this is all stuff in computer vision because people were interested in learning what or understanding what are the different layers doing in a convolutional network. And they discovered that, well, the first layers are focusing more on edges. The second ones are more, and as you go for, let's say, deeper and deeper layers, you're getting like more semantic and compositional aspects. That is, yeah, uncertain and stuff, right? And there's a big discussion going on. Here, there's this method called regression active modeling, where basically after ingesting and putting all the layers that you might have, you have a regression layer in the end, a fully connected layer that basically is turning down and weighing down the different aspects of the variables and the layers. So you can actually visualize what's happening through time. We were again interested in predicting crop yield. In this particular case, was wheat in India, and it was very interesting because you could actually derive this sort of maps, telling you again which are the variations of the different components, the different variables, the different covariates through time, and which were more or less affected by clouds or by floods. Again, monitoring and learning and anticipation for this prediction, forecasting, and impact assessment. There's basically the main application that we may find in the motion scenario. Good. This is super cool, no? Because we are almost there. We are almost there. No, we can explain almost everything, right? We can encode the physics, decode physics, right? And then we can also, explain what's going on. No? Well, not quite yet. No? Why? Because, there's something that happened a year, like 100 years ago. It was unfortunate, and it was, Pearson correlation, right? Pearson correlation flooded the field statistics and machine learning, statistical inference in general for years. And you cannot even pronounce the C word. No, this is how we name it. It's almost forbidden, right? You can say, you have to say something associated with drives, impacts that, right? We cannot say cost based on that, right? Let's see what is going on now in the field of, let's say, pragmatic causality. I'm not going to focus on theoretical causality. This is not my field. I know almost nothing about that, but we try to develop causal inference methods that can be applied in the under certain circumstances, and of course under some assumptions to our field of work. So, sort of a motivation, right? Correlation is not causation, but then what's that? Correlation, what is it? What is it? No, you have this stupid example, right? That correlates the chocolate consumption with the novel prices all over the right? It is almost linear. So you only have to feed your population with chocolate, right? That's good. Right? Yeah, it would be good anyway. Right? So, for this example that this author just published this paper with striking relationship between storks appearance and babies in regions, in some particular region in Germany. And they found that it was the storks are bringing babies. Yeah, I mean everyone could agree on that, right? It's Just an empirical observation. That's good, no? But maybe it is not storks that are bringing babies, or that babies are like attracting storks. Maybe it could happen. Maybe it is something else. Maybe there's a compounder, like, for example, rural areas that are possible, right? Like storks, and people have no babies, yeah, because of whatever reason. Okay, so trying to go a little bit more formal, more formalized, you could have like, given these two variables, like storks and babies, you could basically think of three situations, right? The two unlikely ones, that storks are causing babies, or the babies are attracting storks. Or you could think of this z variable that is actually causing or driving this, right? Well, in the end, everything resorts to the computation and the analysis of this joint distribution. And you can actually summarize it or analyze it in different ways, depending on the factorization you choose, right? You could choose this or the other one. And then both are actually correct. So which one is the right one, right? So this is known as the common cause principle. That says that basically x and y are statistically dependent, and there exists a z variable that is actually causing both. And this is an important concept, right hand mark. Yeah, like 36, 56, I think. Anyways, a very important principle that basically set up the basis of modern causal. And now it is kind of possible under certain circumstances and assumptions to develop methods that can say a word about the causal relation. Why is it important? Well, causal discovery or causal inference is really, really important because it allows you to learn not only that x is good for fitting y, but if x is actually causing y, or it is the other way around. I mean, if you have your emulator or regression problem, and then you reverse x and y, maybe you can do it well. So how we actually do it. So what is good for? I mean, causal discovery or causal inference is good for many different things, especially in the Earth side, system side. For hypothesis testing, we are always doing assumptions. This can drive that, maybe the El Niño event is driving moisture in this area, temperature rises because of that. So we can check this with observations and algorithms. Also for comparing models and data, right? Because I've seen before that our data and our simulations are either very scarce or very massive. And in any case, they have some kind of structure, spatial temporal structure. And comparing these very uneven sample cubes, it is really, really hard, right? Even with modern statistical techniques, no, that try to, find a kind of manifold embedding or dimensional background, whatever, it is really hard to compare them. So comparing them to the development of causal graphs, that could be a good approach. And then the third thing, let's say, very impactful and very useful question that we should address with causal discovery would be trying to discover what are the causes of extreme impacts or extreme events. For example, years ago, we were suffering a severe heat wave, and actually talking to my people in Valencia, they were suffering. They were 40 degrees, something like that. What is going on? I mean, is this just because of this iron dust that is coming up, or is just probably used by climate change or not? So can we actually discern or attribute the causes, the real causes of the events that we observe? Okay, so there is a bunch of methods, and with some colleagues, we published these two papers. Showing you here on the slide. The first one is about the characterization of the time series in your system sciences. It is important to note here that we are in this particular paper. The first one, we are practicing only on time series. Okay. On the second one, we are approaching the field of what happens when you don't have time involved. It is a bit counterintuitive, no? Because everything He has always argued that time is the only substrate of precision, right? What happens when you don't have time involved in the processes that you want to study? So there are kind of methods for tracking this problem. So here you will see like 4 different methodologies that can be applied. I will go through them just with a pragmatic example of each one of them, so you can more or less grasp what we're doing. The standard one is stranger causality. This is a very old method, awarded to stranger. He was awarded with Nobel Prize in economics in 55, I think that's 52, but this is a very, very intuitive method. And while people have argued that this is not actually causality, it's more about predictability, right? So if you have X and Y and you're able to predict Y from the past of Y, better than from the past of X and Y, is because there is no causality. Right? And if you can do it the other way around, maybe you can argue that there is some great causality. I said great causality, and I can say causality because good news myself. This is I cannot tell you around the world, right? So you have to speak properly, and this is like range causality. So there are other methods called nonlinear space methods. And I will show you an example again. It is more dominated by the fields of state-space methodologies and the factor modeling. And you will see in a second. Of course, the third approach has to do with this motivation that I showed you about the stars and the babies, about how to factorize the PDF and how to actually estimate conditional independence, how to do that properly and efficiently, and what happens when you have time costs. Okay? And the fourth one is related to structural causal models. I will show you a very, very simple one that we actually evolved in this second video. Okay, let's go on. The first approach, the standard range causality. So you have a 10 series, well, a couple of 10 series, so many 10 series, right? X, Y, Z, 1, Z2, whatever. And then the idea here is just to develop 2 models. So you predict the future of Y from the past of X, or you predict the future of Y from the past of X and the past of Y. Okay, and then you just check the children who is performing better. That's it. Super simple, neat, clean, right? But then this methodology suffered from 2 main big assumptions, I would say, stationarity and linearity. Right? So what we proposed recently was a method based on internal methods and EPPs that can cope with those. Non-stationary processes that often occur in the artificial science and the linearity, obviously, because of the nature of phenomenon. But the approach was very similar, right? It is, we call it the explicit range causality or cross-informational. So here I will exemplify this in a very, I would say, clear example of why correlation is not this range causation, right? So look, here we are interested in analyzing the relationship between what are the impacts of a linear event that happens around this area in the Pacific Ocean, and what is the impact on the soil moisture on land? Is it actually impacting or not? What measure? Right? So here you have on the left-hand side, you have this map showing you the correlation, the time lag correlation between the linear time series and the soil moisture time series. So you can compute. When is the maximum time lag correlation? And then you can find like many different great regions that are actually impacted positively or negatively because of the mean, right? Yeah, okay, fine. But then what happens when you apply this nonlinear range causality, or even with the range causality, a lot of detections are actually identified as spurious. They are not really useful for prediction. So they are not really useful for assessing range causality, right? And this is what happens. only the green dots are, sorry, the green circles are the only ones that are actually range causal. And the red ones are not really range causal, they are just the previous relation. So as a conclusion, I would say that causality is a sharper indicator of the kind of correlation. And in this case, we could only retain like the real range causes of soil moisture in very dry and extreme ecosystems, or in very wet ecosystems like in the tropics. They were the only situations. And the others, it was not conclusive. We could say something. Okay, then another approach, also for time series. Okay, so here the idea is interesting and it has been applied vastly in many different situations. This is called convergent cross mapping. So essentially, CCM develops or approximates the manifold of X, manifold Y, and tries to answer the question if there is some kind of information footprint effects on Y, or manifold effects on Y. So it does a lot of regressions, local regressions from the nearby points in X goes to the Y point and the other way around. And this is done with an increasing amount of data around the locality of the submanifold that we are trying to explain. And then the argument is that with more data, the convergence, that's why the convergence here appears. The convergence is still kept. I mean, the difference between the correlation going one direction or the other is still kept, is because the information of X is actually impacting the Y. So there is some information footprint of Y, so you can actually claim that Y is caused by that. So this is a good method, but again, strong assumption. Right? The first clear, strong assumption is that you only need two variables. Yeah. You only have two manifolds, you only need two variables. Now, this is quite disturbing, right? Because what happens with the Z variable, no? Impacting storks and babies, no? So, well, you have to assume that you can actually recover the manifold structure from private differences and from only one variable, and the relationships are only. The second big assumption, or I would say caveat of this method, is that it is very sensitive to noise. It has like a lot of hyperparameters. And what we did in that particular paper was to address some of these issues essentially by connecting the dots, connecting this method with information geometric criteria. We connected those, and then also in order to get rid of this sensitivity to noise, we applied the methodology with a bootstrap resampling technique that could alleviate more or less the instabilities of the method. We apply it to, again, global cubes, and in this case, we could learn some relationships between photosynthesis, temperature, and moisture, and we could derive causal maps. Right? We could say, okay, in this particular region of the very dry or water limited regions, the gross primary productivity and the synthetic activity of plants and vegetation is caused by moisture, or at least limited by moisture. Temperature is only important or causing impacts in boreal regions, in those variables, and the GDP is affected by moisture in this particular case, like savannas or grassland. You could say something like this. Of course, there is always, the fear that you cannot actually validate that, other than looking at and talking to them next to it. Okay, things look like a reasonable pattern. Maybe this is not that right, because maybe there is another variable, another confounder that you did not incorporate it in your pipeline, and you should. This kind of thing. Right? Okay. And then the third approach we have to do with the estimation of conditional independence. So you only want to check if X is causing Y is causing X, given Z, right? A very simple approach that was presented some years ago. and essentially relies in this case on linear regression. So you only have to assume two linear models. So you look at the x from z, y from z, and then check if the residuals are correlated or not. And that's super smart, super easy. A very simple conditional independence. Very simple. What happens? Of course, you can argue, okay, it's linear. No? So what can we do when you have these nonlinear shape dynamic distributions? I mean, this is just 2D, no? But you may imagine what happens when you dimension. So an approximation or an alternative is of course using nonlinear method for the interpretation. So you learn x from a Gaussian process with z, y from z with analogy b, and then you test independence of the residuals. Likewise, in this case, the authors they use the distance correlation coefficient, and it is costly, and it has some parameters, tricky parameters to tune. And yeah, when you replace the distance correlation coefficient with basic, it becomes a bit more stable, not super stable, but stable. And people have been using this in schemes called PC. The PC scheme is an efficient way to browse and to analyze a whole graph of many different variables to identify which are the variables. It's very efficient because you can see that as the number of variables increases, the graph increases, and the amount of combinations explodes. So here in the PC algorithm, we can actually nicely. There is a method called PCMCI that essentially adds like this condition on instantaneousness. Okay, so the traits of potentially instantaneous. And this method, PCMCI, is being quite used in the community, both in earth sciences and climate sciences. And in this case, people use that. I mean, our colleagues here in Germany, they use that for comparing models with observational data. So you know that you have climate simulations coming from different models, and then you have the observational world. And then instead of comparing cubes, you want to derive a causal graph. Here, climate simulation or observation. And then you have like you end up with a causal graph here, and then you compare the edges. Are these figures matching or not between the models, across the models, or between each model and the observation? So you can say something about what are the most plausible models in there when it comes to the comparison to causally, not just in terms of correlation or information. Okay, and then just to end up, the fourth family is called structural causal models. Comes back again to this question of how do we factorize these joints? And the idea is very, very simple. I like it very much, to be honest. It has to do with this idea that the cause should be actually independent of the mechanism that is passing, or the generating mechanism, I mean, the function that is passing x to y. Okay? So if we assume in this plot that x is the cause, and you have a generating mechanism of y, then it becomes pretty clear that this funky distribution of y could not actually derive cause the distribution of x. It is more plausible the other way around, right? So here the idea or the motivation is to assess the independence of the independence of the generating mechanism, right? Independence of this function. So how do you approach this in a very, very neat and simple way? So this is a classical motivational example. So you have the altitude of a bunch of cities in the world and the temperature, and their temperature, right? So it is obvious because of physical laws and because of common sense, if you want, that altitude is causing temperature. I mean, it will be absurd, no, to think that the temperature of the cities is causing the hot, no? Maybe just they are on top of a volcano. I don't know. But anyway, so what they do is essentially to feed two models. So predict temperature from altitude, predict from temperature. Probably the accuracy will be pretty much the same. And then what you do, the second step is you have to plot the residuals and check if the residuals of the forward or the backward model are more or less independent of the potential cost. In this case, on the left, you have the temperature residuals compared to the altitude, and then on the right, you have the altitude residuals compared to temperature. And you can see that here on the right, you basically, just by naked eye, you see more structure. So there's more dependence here, no? So you're missing something. You're missing something. There's a structure in the residual. In there, the residuals look like more independent of the cost. So that's why you actually say that this is the right also direction. So we did apply it to many different problems in Earth and geosciences, where we actually have ground truth, so altitude, temperature, altitude, precipitation, etc. But also in order to compare models with observational data, and also to assess what are the intrinsic parameters that you have to fit rather to come to models to behave like more realistically, more causally motivated. And the results are kind of good. I mean, it's not super fantastic. You have AUCs of 0.6, 0.7, something like that. Quite uncertain, of course, but the community is evolving of these bivariate problems very, very dramatically in the last 5 years. I would say that there are like hundreds and hundreds of papers evolving these ideas to detect the right direction. Yeah, and I wanted to finalize with this field that we are super excited in Valencia that basically joins forces of deep learning, finite sciences, and causality. So why not? And the main motivation is not just detect position, but to learn feature representations that are causal. Okay, which is a different thing. And the method should be amenable, should be useful in the end, practical for the data cubes that you get that are spatiotemporally correlated. No? In this case, for example, in this picture, in this cartoon, you have some regions, some variables, for example, temperature on the left and precipitation on the right, that are mutually causing each other at different time scales. And you can see that the connections are also not only positive or negative, but also time dependent. So something causes something at different time scales. So it is quite a complicated problem because the processes or the causation happens at different spatiotemporal relationships and different multivariate variables. So what we did here was this approach. This is the problem that we're concerned about. So again, what happens? What are the causal drivers of ENSO, of El Nino again? Through time, you have a time series that is summarizing the surface temperature in Russia and the Pacific Ocean. And how is this actually, this anomaly is impacting greenness in Africa, which there's a lot of debate and many papers debating about what are the actual regions impacted by this event. So we have cubes and we have time series, right? And this is the algorithm that we just came up with. So the algorithm is very simple. So you have an encoder decoder. Then you learn a latent representation. This encoder decoder just learns to reproduce or replicate or reconstruct the bits of NDVI, the representation index. But then on top of that, we want that this latent representation should be causal, but Granger causal. Okay, so you can decide the Granger causal, the Granger causal index, right? It is basically a ratio of the variances of the residuals that going in one direction and going in the direction of the latent representation should explain itself, or versus the latent representation should be predicted from its past plus tensor, right? So you compute this as a ratio, plug it as a one more term in the loss, and then cross fingers, of course, and then you expect that the latent representation should be going to causal.
One question. Yes, on the one side, because here one ratio works in one direction. You do it twice, one ratio and the other one. Good question. Good question.
I think that we do one, but this already has been changing quite a lot in the last weeks, I would say. Because we are no longer, for example, we are no longer using autoencoders, but the rational encoders. At the very beginning, we only used one latent, and we are now using a combination of latent. So yeah, but concerning the index, I think that we are only using one. Okay, yeah, one direction. Yeah, because in principle, you know that you should assume something that tensor precedes the impact, right?
And if it fails, it means
Yeah. But in any case, you are incorporating this parameter, beta, in this case, that can trim down the impact of the green default. And actually, it fits kind of reasonably well. So it is very sensitive, of course, but you can achieve latent representations that are more similar to the answer or not, right? By tuning this parameter. And then what? Okay, again, we are facing these deep learning architecture, and you have latent representations, but okay, you get these crazy funky curves, and then what, right? So we need to know, right? So what we did is, explainable AI. So now in this little monster, we have everything. We have causality, explainable AI, deep learning, everything, right? So we applied integrated gradients on the encoder, because in principle the encoder has been trained to be not only good for finding latent representation that reconstructs one, but also that it is going to cause, right? So you apply the integrated gradients, and so you can derive maps, especially explicit maps of causal interaction. And then, of course, it is nice because you can see the differences on the right, on the top versus on the bottom, where you don't have this range of cost impacts. It impacts quite noticeably. Then you can find some regions that are actually affected and that they were not reported before, right? And then you can go and analyze by biome, let's say, by types of forest, types of vegetation, and you can say something like that. Okay, but causality is not easy. It's not really easy, and it is very typically tailored to particular application domains. So what we decided is to promote this platform that we are developing, and this platform allows you not only to evaluate models, but now very soon we'll be able also to train causal models itself and allow interaction with the user. So the idea is that you will be able to upload your data set, and the platform analyzes the data set, proposes some sort of a bunch of causal graphs, and allows you to interact with the user, who is the expert in this case, and allows you to evaluate the user in most possible. But feel free to use it. And you can download current data, apply your causal graph, causal discovery methods, and then upload the solution. And since we know the ground truth, we can evaluate this. And that brings me to the end of this lecture. The main conclusion is obvious. It is not enough. And I would like us to end up with reminding you these 3 sentences, very common in statistics and machine learning, right? The first one, you know that you can be right for the wrong reason. So that is actually calling for more plausible, more consistent physics-aware machine learning. The second one is a standard box sentence or just having saying that all models are wrong, some are useful. But what is usefulness if you don't know what the model is actually doing, right? So it's actually calling for explainable AI. And the third one is an informal one that is typically sometimes ICML and read that people can come on, AI is not that big learning here. So artificial intelligence is much more than just fitting, right? So let's go into causal discovery algorithms or learn an abstraction or data causal representation. So yeah, give physics, shot, and causality a chance, and that was it. Thank you very much.